Hey there. In this video, we are going to talk about logarithmic properties. So there's a lot of properties of logarithms that we can use, and these become particularly helpful when you're trying to solve log equations. So in this section, we're just going to practice with manipulating logs, condensing and expanding them so that later we can solve equations using these properties. So there's a number of properties, and they might sound kind of familiar or feel familiar if you start thinking about exponent rules. These work pretty similarly because of their relationship to exponents. So the first one is the product rule. If I have a log, and all the bases have to match for this, so I just have a generic log base A for each one of these. If I have the log of x times y, if I wanted to expand that out, I could write these as two separate logs that are adding. So if it's multiplying in one log, then I can rewrite that as log of x plus the log of y. And I can also condense. So if I had the sum of two logs with the same base, I could condense it down to a single log where those arguments are multiplying. Next one is the quotient rule. So if I have two things dividing in a log, I can separate this into separate logs where it's subtracting now. Excuse me. So the numerator would come first minus the log of the denominator. The third rule is the power rule. If I have an exponent on something inside of a log, I can pull that exponent out front and it multiplies by the log. So the log of x to the r is equal to r times the log of x. Some other properties that are useful are inverse properties. Because exponentials and logs are inverses of each other, they undo each other and can be used in solving equations. So if I have a to the log base a of x, the log and the exponent there just kind of cancel out, and I end up with just the argument of x. Same thing if it's reversed, the log of a to the x is equal to just x. Some properties of 1 that are helpful is to always remember the log of 1 is equal to 0, and the log base a of a is always equal to 1. And that one makes sense because really, if I were to translate this into an exponential, it's a to the first equals a, which makes sense. Okay, so let's get some practice with using some of these properties. So here I've got 4 different expressions. We're going to expand them all out. So I want to break these up into as many logs as I can and simplify where possible. So the first one, log base 8 of 64 times 6. Well, they're multiplying, so I can use that first rule, the product rule, and split this up into the sum of two separate logs. So that becomes log base 8 of 64 plus log base 8 of 6. And the only way I could simplify this further is if either one of these logs happen to evaluate to a nice number, which it turns out that since 8 squared is 64, log base 8 of 64 is 2. So I can simplify that first log to just 2 to give me give me 2 plus the log base 8 of 6. All right, next one, I've got log base 3 of 27 over x squared. So here I can use the quotient rule since they're dividing. So this becomes log base 3 of 27 minus log base 3 of x squared. 3 to the third power is 27, so log base 3 of 27 is going to be 3. And I can also pull the 2 on the x out of that log and multiply it out front. So this becomes 3 minus 2 times the log base 3 of x. And I used a couple of rules there. The next one is log base 5 of the fourth root of 11. So here it might look like, gosh, there's nothing I can do. But if we remember that a root can be rewritten as an exponent, I can rewrite the fourth root of 11 as 11 to the 1/4, and then I can use the power rule to pull that exponent out front. So this becomes 1/4 log base 5 of 11, which is a lot nicer looking, a lot less intimidating, easier to work with than what we started with. Now the last one takes all these rules and really throws them together. So it's going to take a few more steps to get through this one. I have log base b of xy cubed divided by 5z squared. Okay, and usually the order you deal with these makes things a lot easier. I'm going to start by dealing with the quotient. So I'm going to break this up into two logs that are subtracting. So log base b of xy cubed minus log b of 5z squared. Now, each of these logs have a product in them, so I can break them up. Just remember that that negative on the second log is going to follow both of the logs this breaks down into. So using the product rule, I get log b of x plus 3 log b of y if I pull the exponent out at the same time, just to save me a step of having to rewrite this. Minus, and then both of these logs are subtracting, so I get log b of 5 minus 2 log b of z. And I use that power rule to pull the 2 out. So really not much more to do here. I'm going to go ahead and distribute the negative to those last 2 logs. And there's not really much else that I can do. There's a lot of variables in here, so none of these can really be evaluated. And I don't even know what the base is. So there's nothing more I can do. I've expanded it out as much as possible. The next thing we want to look at in this section is the change of base formula. I've mentioned previously that your calculator has a common log and a natural log function key, but it doesn't have, for most calculators, it doesn't have a choose your own base kind of function. You might find some out there, depends on the model you're dealing with, but for the majority of calculators, there is only a common log and natural log key. So this change of base formula allows us to take any base and convert it to one of those bases, or any base we might need it to be. Okay, so this one says if I have a log base b of m, I can convert that to a new base n by transforming it into log base n of m divided by log base n of b. So it's log of the original argument divided by log of the old base. And that looks a little overwhelming. If I rewrite it using common log or natural log, it looks a little nicer. So log base b of m can be put into a calculator or changed to log m over log b. And if I wanted to switch it to natural log, it would be log m, or natural log of m over natural log of b. So either one of those keys can work. You can test it out with some specific values. You get the same answer whether you convert to common log or natural log. So let's give this a try with a couple of examples. So I want to evaluate each log using the change of base formula. And we're going to approximate our answers to 4 decimals. So you absolutely need a calculator to do these 2 problems. The first one is log base 11 of 2. So if I convert that to common log, that would be log of 2 divided by log of 11. And I can plug that into my calculator to get a more accurate answer or an approximation. And so if you test this out with your calculator, you should get about 0.2891. And the last example here, log base 3 of 6. Let's say I want to convert that to base 10. So that would be log 6 over log 3. And plugging that into a calculator, and make sure when you do plug this in, if you have a calculator that when you hit the log key opens up some parentheses, make sure you're closing those off before you divide so that it is dividing by the right values. So this one you should get about 1.6309.